Welcome, everyone, to our very first lecture on the principles of ecology. Today, we are going to explore one of the most fundamental questions in biology. How do populations grow? Whether we are looking at a microscopic bacterial colony on a piece of food or a herd of deer in a vast forest, the rules of nature dictate their survival and multiplication. We will uncover the mathematical secrets behind these changes, starting from idealized scenarios of unlimited resources all the way to the harsh realities of environmental limits. Let us dive in. To begin our journey, let us imagine a scenario where a population has absolutely unlimited resources. Think of a few bacteria landing on a fresh, untouched piece of food. With endless space and zero predators, there is nothing to stop them from multiplying. This is what ecologists call exponential growth. It is a situation where the per capita growth rate remains perfectly constant, no matter how large the population gets. Because every single individual continues to produce the same number of offspring, the total population size explodes in a very short amount of time. Understanding this helps us measure a species' biotic potential, which is its maximum capacity to reproduce under perfect conditions. Now that we understand what exponential growth is conceptually, let us look at how it works mathematically. To describe this explosive growth, ecologists use a simple differential equation. This formula tells us exactly how fast the population is changing at any given exact moment. The term dn over dt represents this rate of change, essentially how many new individuals are added per unit of time. This equals r, the intrinsic rate of increase, multiplied by n, the current population size. The intrinsic rate, r, is simply births minus deaths per individual. If r increases, the population grows much faster. And as n gets larger, the number of individuals added per time step becomes absolutely massive. This formula we just saw leads us to an important question. How do we find the exact population size at a specific point in the future? While the previous equation tells us the speed of growth, we must use its integrated form to predict future numbers. In this powerful formula, n sub t represents the future population size. We calculate this by taking n sub 0, which is our initial starting population, and multiplying it by e raised to the power of r times t. The letter e is a mathematical constant, roughly 2.718, that naturally appears in continuous growth processes. This shows that the future population compounds continuously, depending heavily on how long it has been growing and the intrinsic rate of growth. Before we move on, let us see this with a concrete example. Suppose a scientist places an initial population of 100 bacteria into a nutrient-rich petri dish with unlimited resources. The intrinsic rate of increase is 0.5 per hour, and we want to know the population after 4 hours. Because resources are unlimited, we use our integrated exponential equation. We plug in 100 for the initial population, 0.5 for the rate, and 4 for the time. Multiplying the rate and time gives us an exponent of 2. The constant e squared is approximately 7.389. Multiplying this growth factor by our starting 100 gives 738.9. Since we can't have a fraction of a living bacterium, we round to exactly 739 bacteria. This proves how rapidly a population explodes under ideal conditions. Now that we have calculated this explosive growth, let us visualize it. What you are looking at is the classic J-curve of exponential growth. On the horizontal axis, we have time, and on the vertical axis, we have population size. Notice how the curve starts off relatively flat. This happens because the initial population is small, so the absolute number of new individuals added is low. But suddenly, the curve shoots straight upward. As the sheer number of reproducing individuals becomes massive, the population skyrockets. This graph perfectly illustrates a species' biotic potential in an idealized environment, where intense competition and disease simply do not exist. While the J-curve is fascinating, we must now return to reality. In the real world, no population can grow forever. Every habitat on Earth, from a tiny puddle to the vast ocean, has strict physical limits. If we look back at our petri dish, the scientist only put a limited amount of sugar in it. At first, the bacteria multiply rapidly because there is plenty of food. But as the population gets crowded, resources start running out. Waste builds up, and individuals begin competing with each other. This intense competition forces the rapid multiplication to slow down. Eventually, the population size levels off and stops growing completely. This realistic scenario is what we call logistic growth. This realistic slowing of growth brings us to arguably the most important foundational concept in population ecology: carrying capacity. Carrying capacity is the maximum number of individuals that a specific environment can sustainably support over the long term. We denote this maximum limit with the letter K. You can think of carrying capacity as an invisible ceiling imposed by the environment. As a population approaches this ceiling, the per capita growth rate decreases. When the population size exactly equals the carrying capacity, the curve flattens out into a stable plateau. At this exact point, the birth rate perfectly equals the death rate, resulting in zero net population growth. This delicate balance is essential for managing natural resources and protecting endangered species. Now that we understand carrying capacity, let us look at how ecologists mathematically represent this environmental resistance. They took the original exponential growth equation and added a special mathematical term that acts as a braking system. The new equation states that the rate of population growth equals R times N, multiplied by the term K minus N, all divided by K. This new term represents the fraction of the carrying capacity that is still unused and available for new individuals. When the population N is very small, this fraction is close to 1, allowing almost exponential growth. However, as N gets closer and closer to K, this fraction approaches 0. This forces the overall growth rate to slow down and eventually stop completely. Let us apply this braking system to a real-world scenario. Imagine a protected forest reserve that can support a maximum of 500 deer. Currently, there are exactly 100 deer, and their maximum intrinsic growth rate is 0.2 per year. We want to calculate how many new deer will be added this year. We substitute our values into the logistic differential equation. First, we calculate the unlimited growth portion, 0.2 times 100, which gives a theoretical maximum of 20 new deer. Next, we evaluate the environmental resistance inside the parentheses. 500 minus 100 leaves 400 unused spots, which divides by 500 to give 0.8. This means the environment is operating at 80% of its maximum potential. Multiplying 20 by 0.8 gives us exactly 16. The environmental limits actively suppress the growth from 20 down to a realistic 16 deer. Having calculated logistic growth, let us now observe its visual signature. This diagram shows the characteristic S-shaped or sigmoidal curve of logistic growth. Notice the horizontal dashed line at the top? This represents the carrying capacity, K, the absolute ceiling imposed by the environment. The solid curve begins with an exponential phase, where growth is fast, mirroring the J curve we saw earlier. But as resources become scarce, the curve transitions into a decelerating phase. It bends and finally flattens out into a stable plateau exactly at the carrying capacity line. This beautiful S-curve provides a highly realistic picture of population dynamics, showing how nature eventually balances itself when faced with strict environmental limits. We have covered a tremendous amount of ground today, so let us summarize our key takeaways. First, we learned that exponential growth represents a species' maximum reproductive potential under ideal, unlimited conditions, resulting in a rapidly accelerating J-curve. Second, we discovered that real-world environments have limits, which forces populations to follow logistic growth, forming a stabilizing S-curve. Third, we defined carrying capacity as the absolute maximum population size that a specific habitat can sustainably support. By understanding these mathematical models, ecologists can predict dangerous population explosions, manage wildlife harvests safely, and determine exactly how much land is needed to save endangered species from extinction. You now have a solid foundation in the principles of population ecology.